Hello, this is lecture 5 of our direct energy conversion systems for sustainable energy course. And in this lecture, this and the next lecture, we'll talk about the direct conversion of solar radiation to electricity. And the topics we will cover in this lecture are the introduction to band structure. These are some of the these things come from elementary quantum mechanics. And we talk about the semiconductors and the characteristics of the material properties in there, and we talk about the p-n junction, which is the key for the solar cell, and we talk about the band gap effects in relation to solar energy spectrum, and then we talk about the solar cells or photovoltaic cells, and briefly mention the light emitting diodes. First we want to understand what the band structure is, and here in this figure we typical energy spectra are sketched. The spectra of the free electron gas is shown on the left. The energy u to the power of p of the single particle states is shown in the vertical axis. The energy levels allowed by the quantum mechanics start from zero and reach to infinity. The energy levels are spaced many orders of magnitude more tightly together than the lines shown in the figure here in this particular case. Uh, for almost all practical purposes, the energy levels actually form a continuum. In the ground state, that means it is at absolute zero temperature. The electrons fill the lowest of these energy levels, one electron per state. And in the figure, the occupied states are shown in red in this particular case. For a microscopic system, the number of electrons is practically speaking infinite, and so is the number of occupied states. The diametrically opposite to the free electron glass picture is the case that the atoms of the solid, which are spaced so far apart, we can essentially consider them as the lone atoms, and widely spaced atoms do not conduct electricity, assuming that not enough energy is provided to ionize them. While for the free electron gas, conduction can be achieved by moving few electrons from the red region to slightly higher energy levels. And for lone atoms, there are no slightly higher energy levels for them to move. So when the lone atoms are brought closer together to form a true solid, the discrete atomic energy levels broaden out into the bands as shown in the metal here. In particular, the outer electrons start to interact strongly with the surrounding atoms. The different forms that these interactions can take produce varying energies, causing initially equal electron energies to broaden into bands. In fact, you can see these lines come together in a band structure. For metals, now the conduction is now possible because electrons at the highest occupied energy level, the Fermi energy, in this particular case, you can see the tick mark here, can be moved to slightly higher energy level to provide net motion in a particular direction. This is likely that they can, for a free electron gas, as discussed as before, the net motion can produce current. Insulators, on the other hand, are very different. They completely fill up the highest occupied energy band in this shown in this figure here. That filled band is called the valence band. So all this filled band is called the valence band. The next higher and empty band is called the conduction band. So here, this is the, for example, this is the Fermi energy. So this in the red lines which comprise here is called the valence band, is full of electrons, and the conduction bands, no electrons are can exist. To create a state with net motion, some electrons would have to be moved to the conduction band. but that would require large amount of energy to overcome the band gap, which is indicated by E to the power of P to the gap. This is the energy of the band gap. The minimum energy required is the difference between the top of the valence band, which is this line, for example, here, and the bottom of the conduction band, which is indicated by the marker in this case here. It is typically of the order of electron volts, comparable to atomic potentials for outer electrons. This in turn comparable to ionization energy is a great amount of energy on atomic scale. So in essentially, if you look at these pictures, and the quantum mechanics allows only discrete energy levels as indicated by these lines here for the electrons in a solid, and these levels group together in bands with the gaps between them. Uh, in fact, if you look at the Fermi energy, which is typically in the middle of the valence band and the conduction band, and it is given by the expression which is shown here, and which is proportional to the number of electrons per unit volume, and the electron mass is given by here, and h hash is the uh, reduced Planck constant. So by knowing the number of electrons per unit volume, you can find out what the Fermi energy is, and this actually can be found out as we will see in the later slides. Now, what we now move to the spectra when it is non-zero temperature. So when this is essentially when previous spectra was seen, this is seen at the absolute zero temperature, and this is now given at non-zero temperature. And temperature can have a significant effect on electrical conduction. Higher temperature decreases the conduction in metals, and as there are more crystal vibrations that move electrons can get scattered by. But a higher temperature also changes which energy states the electrons occupy, and that can produce what is called semiconductors. The energy states previously shown were at absolute zero temperature. In that particular case, there are no electrons with energies above the Fermi level. But here, at non-zero temperature, there is now some random thermal motion that allows electrons to reach energy levels up to roughly the factor kb times the T. So that is proportional to essentially T above the Fermi level. So you can see that there is, in fact, the tick mark is right here. There is some electrons above that, where kb is the Boltzmann constant and T is the absolute temperature. The change in electron energies is described mathematically by the Fermi-Dirac distribution, which we will not discuss it here. However, for an insulator, it may make a dramatic difference if the band gap is not too large compared to this way kb times T. Random thermal motion will put few lucky electrons in the previously empty conduction band, and that is actually what would happen in a non-zero case. These electrons can then be prodded to slightly at higher energies to have some electric current to flow. And while the electrons move into the higher band, they create holes in the valence band in the region which is considered to be red. They states that have lost their electrons allow some electric current. Valence band electrons can be moved into holes that can have a preferred direction of motion. In this case, when there is a hole is placed, then they can move into that hole. These electrons then leave behind holes that have the opposite direction of motion. It is often more convenient to think of the moving holes instead of the electrons, as the electric current carries in the valence band. Since the hole means that negatively charged electron is missing, a hole acts much like a positively charged particle would. And because both the electrons in the conduction band and the holes in the valence band allow some electrical conduction, the original insulator has turned into what is called a semiconductor, and that is what is represented in this particular case. So for semiconductors, conduction can occur because some electrons from the valence band are thermally excited to the conduction band. And both the electrons that get into the conduction band and the holes they leave behind in the valence band can conduct electricity, and that is what is described in this section. Now, if you look at the number of electrons, the average number of electrons for single particle state for non-zero temperature is given by this expression here, where you can see d sub p is the energy of the particle, and mu is the chemical potential, and this is the Boltzmann constant times the temperature plus 1. And this is the expression for the average number of electrons for the single particle state. Now, if you look at a little bit more detail, what I just briefly described is given again in here. And as like we have shown these discrete bands here, and this is the valence band, this is the conduction band, and the gap here is the band gap. And then as I described previously, when you electrons moves up, if the energy, for example, if you shine with solar light, there is enough energy in the spectrum. It has the ability to move the electron into the conduction band. When that happens, the holes will form, and of course holes can migrate in the sideways, and that is how they allows the movement in this in the semiconductor. And the energy gap is given by this expression here, delta, and is represented by electron volt. That is energy acquired by one electron moving through a potential difference of 1 volt. And in an insulator, this gap can be very large. So the electron concentration in the conduction band are extremely small, therefore also the electric current. In a semiconductor, on the other hand, the band gap is small enough. There will be a significant electron concentration in the conduction band. This increases as the temperature increases. And for example, when the photon is absorbed in the semiconductor, this is shown here, and there is a Fermi level is right in the middle of the red color here. When you hit with the photon, they transfer that photon will excite the electron and transfer the energy, and then the electron will jump across to the band gap into the conduction band, and it is free to move in the solid when once it reaches there. But however, the photon must carry more energy than required to transfer the electron across the gap. And we will discuss this further in relation to the solar spectrum. And the electron that has been excited in the conduction band leaves a place in the valence band that is now occupied by the electron. Such an empty space is called the hole, and that is a positively charged particles. The interaction between the energized electron and the hole it leaves behind is called the exciton, and the difference in energy levels between the hole and electron is also known as the typically the band gap. Now, in coming back to our original schematic, and when you look at the semiconductors, that is represented by this is the valence band here, and these are the different states in this case. And the horizontal coordinate here shows the density of the states, that is the number of quantum states per unit energy range. So that is essentially number of quantum range, and you can see they have a distribution here. And then you have the valence band, that means there's more electrons on the lower side compared to the higher side, and this is the band gap. And in a non-zero state, you can see some electrons, insignificant amount of electrons appearing in the conduction band. The vertical coordinate here shows the energy of a single electron quantum state as before. There are no quantum states in the band gap, as we have been talking about. States occupied by electrons are shown as before in the red color. At room temperature, there are some thermally excited electrons in the conduction band, and those are these typical small red marks shown in the conduction band. They left behind some holes in the valence band. Both the electrons and the holes can provide electrical conduction. However, the number of such electrons and holes is very much smaller than what is represented in the figure. The number of electrons per quantum state, which is given by this expression at the bottom here. In the conduction band, this expression can be simplified into Maxwell-Boltzmann equation in this particular case, and it shows that the conduction band, the electrons are extremely small. The number of electrons per state in this particular case is given by this expression here, where the T here is the absolute temperature and Kb is the Boltzmann constant, and this is the chemical potential. For an intrinsic semiconductor that is represented here, the Fermi level is about in the middle of the band gap. So the average number of electrons per quantum state at the bottom of the conduction band is given by this expression simply here, and this is the band gap energy, and these two are this is the temperature, and this is simply constant. At room temperature, kBT is about the product of these two terms is about 0.025 electrons, while for silicon the band gap is about 1.12 volts. That makes m sub e, the number of electrons, about 2 times 10 to the power of minus 10. That's about 1 in a 5 billion quantum states in the lower part of the conduction band has an electron in it. So this is extremely small. And of course, as you go up, the electrons becoming smaller and smaller in the conduction band. So the number of electrons which are shown in the conduction band extremely small. As a result, semiconductors are essentially a bad conductors. So, for example, the way to improve in such a situation, because this is essentially a bad conductor, to make it useful material, what you can do, suppose you have a semiconductor like silicon that has 4 valence electrons per atom. If you replace a silicon atom in the crystal by a stray atom of a different element that has 5 valence electrons, and that is represented in this figure here, then that additional electron is mismatched in the crystal structure, and then it can easily become dislocated and start moving around through the conduction band. That allows additional conduction to occur. Even at a very small concentrations, such impurity atoms can make a huge difference, as we'll find out. For example, you can increase the conductivity of the silicon by a factor of 1,000 by replacing 1 in a million silicon atoms by a arsenic one in this particular case. So essentially what we do is we introduce here a stray atom, and that improves the conductivity of the semiconductor. Alternatively, you can replace silicon atoms by impurity atoms that has only 3 valence electrons. That creates holes that can accept valence band electrons with a bit of thermal energy. Therefore, such impurity atoms are called the acceptors. In this particular case, this is shown in the figure to the right. And the holes in the valence band from which the electrons were taken allow electrical conduction to occur. Because the holes act like positively charged particles, the doped semiconductor is called the p-type, and the donors, which is included in the donor electrons here, this is called the n-type material. So n-type and p-type materials are essentially the materials which are impurities are added in one particular case in the conduction band, and the other one is in the valence band. So if more donors are added, for example, the Fermi level will move up, as you can see here. In fact, the Fermi level in the intrinsic semiconductor is given right in the middle. The donors are added, that the Fermi level will move up. Light doping, maybe an order of 1 impurity atom in a 1 million can do such a movement in the Fermi energy. The upward shift in the Fermi level in the n-type material has another effect. which is it decimates that already miserably small number of holes in the valence band. So the number of conduction band electrons provided by the valence band become bathed in what is called a black body radiation. A very small but non-zero fraction of the photons of the radiation have energies above the band gap. These will move valence band electrons into the conduction band, thus creating electron hole pairs. In equilibrium, this creation of electron hole pairs must be balanced by the removal of an identical amount of electron hole pairs, and the removal of pair occurs through recombination, in which a conduction band electrons would drop back into the valence band. So what we have to do is, when these things jump into the conduction band, you have to take them out very quickly, otherwise they recombine and they regenerate. So the doping of a semiconductor with a donor atom greatly increases the number of electrons in the conduction band, and it produces an n-type semiconductor. And doping a semiconductor with acceptor atoms greatly increases the number of holes in the valence band. It produces a p-type semiconductor. And so when you bring these two together, then it becomes a very effective conductor for all the practical purposes. In summary, you can, and of course, before we do that, the number of holes per state in the valence band may be written in this form here. And in the valence band, the energy level is less than the Fermi level, and the number of holes is nothing but 1 minus the number of electrons. So the summary here is that semiconductor have much too few current carriers to good conductivity, and by adding these doping materials, the conductivity of semiconductors can greatly improve. And that is shown pictorially in this plot here. This is a summary of what we have learned. This is the vertical axis is energy level, and you go in the horizontal, you have this is the Fermi level, this is the band gap, representation of the band gap, and you have the valence band and the conduction band. This top is the conduction band, this is the valence band, and this is the pure semiconductor, which have very little conductivity. When we doped semiconductor is shown here, as we talked about previously, you can see that the Fermi level is much closer to the bottom of the conduction band, and this of course is the conductor. So essentially what we have learned here is the semiconductor has to be doped with materials like boron and phosphor, which is typically used in silicon, and that will make these two different materials and improves the conductivity of the semiconductor.